In this video, I'm going to look at sketch graphs using transformations. The particular transformation that I'm going to focus on in this video is dilation. This video is also going to focus on curves of the form y equals a e to the kx, so on exponential functions. Firstly, let's have a look at our basic graph of y equals e to the power x, and just make a note of some of the features. Firstly, let's label the graph. Secondly, let's have a look at the scale that I'm using here on both axes. Notice that the x-axis has a fairly large scale, whereas the y-axis has a smaller scale, so there are much larger numbers on the y-axis. If we look at a couple of points on the curve, let's take a look at the point where x is equal to 1. Obviously the y value at that point is e to the power 1, or just e. If we look at the point where x is equal to 3, we'll see that the y value is equal to e cubed, which is pretty close to 20, but not exactly, just slightly more than 20. Just make a note of those points. Now let's have a look at the curve of y equals 3 e to the x, and have a look what happens to those points on this curve. Firstly, let's label the curve. Secondly, let's have a look at the point where x is equal to 2. On the first curve, that point will be equal to e squared. On the new curve, that point will be equal to 3 times e squared. So we've stretched the y ordinate by a factor of 3 in the y direction. And of course that goes for all the other y ordinates as well. So you can see that the graph of y equals 3e to the x merely dilates the original curve by a factor of 3 in the y direction. Now let's have a look at y equals e to the 3x. Firstly, let's plot the curve and label it. Secondly, let's have a look at what's happened to our original points. Where x used to equal 3 and the value on y equals e to the x was around about 20, you'll notice that that point has now moved to the left, and y equals e to the 3x, it's equal to 20 at the point where x is equal to 1. So you can see we've sort of squashed up the graph by a factor of a third in the x direction. In fact, every point on the curve has squashed up by a factor of 1/3. Let's just have a look at what happens to the left of the y-axis and zoom in on the two graphs. Here I've zoomed in on what happens to both those curves just to the left of the y-axis. Let's firstly label the curve so we know which is which. The top one is y equals e to the x, the lower one y equals e to the 3x. And you can see at the point where x was -1, on the original curve y would be equal to e to the -1, or 1 over e. On the new curve y equals e to the 3x, at the point where x is -1, that's now equal to e to the -3, much smaller than our original curve. And so you can see that the new curve, y equals e to the 3x, sits below y equals e to the power x to the left of the y-axis, whereas to the right of the y-axis it's above the original curve. The overall effect, of course, is to squash the graph up by a factor of a third from its original x value, so it's squashed it by a third in the x direction. So in summary then, our graph of y equals 3e to the x dilates the original curve by a factor of 3 in the y direction. Our second curve, y equals e to the 3x, dilates it by a factor of 1/3 in the x direction.
For more free tutorials and the PDF for this tutorial, visit www.handwrittentutorials.com.